the FaaS flow and FaaSGraph have been published and ASPLOS 2022 and 2024. And so Yushi is also looking for a PhD position next year. So if you're interested in hire him, and please reach out to him offline or via email.
Thank you. Can you hear me? Hello, everyone. I'm Yushi, a master's student at Shanghai University. I'm excited to introduce FaaSGraph, enabling scalable, efficient, and cost-effective graph processing with serverless computing. This is our collaborative research by Shanghai University and National University of Singapore. Firstly, we're going to briefly introduce the background of graph processing tasks. Graph processing has become essential in various areas, such as social network mining, recommendation systems, and road network analysis. To meet the specific demands of these tasks, researchers have created targeted frameworks designed to handle a large graphs efficiently in both shared memory and distributed environments. And when deploying these frameworks, users have the option to purchase physical servers or allocate cloud-based virtual machines through infrastructure as a service platforms. Now, graph processing follows an iterative execution flow, which can be visualized through a simple diagram. Firstly, during the preprocessing phase, the original graph is partitioned into multiple subgraphs, with a focus on maintaining load balance and minimizing communication overhead. This phase involves creating and dispatching CSR index and other auxiliary data structures, incurring significant computational costs. Now, during the actual execution of graph processing, a coordinator assigns tasks to each subgraph, primarily specifying which vertices are active in the current round. And subsequently, each subgraph begins its computation by scanning edges and updating vertex values according to user-defined algorithms. And now, after the computation, the subgraphs must synchronize their updated vertex values to maintain consistency, which entails expensive auto communication. And finally, the coordinator gathers the results from the subgraphs and decides whether to initiate computation in the next round. This iterative process continues until no further vertex updates can be made. Now, IaaS-based graph systems often lack the elasticity to manage fluctuating workloads. Here we present a real-world workload pattern for graph processing on a city road network. The blue curve represents the normalized queries per minute over the course of a day. And similar to typical IaaS configurations, we establish a fixed VM cluster setting, depicted by the red line indicating constant resource processing capability. This figure highlights two main issues for IaaS-based systems. First, query spikes can arrive randomly, resulting in a surge in tail latency due to insufficient computing resources. And second, during periods of low workload, a significant amount of computing resources would remain underutilized. So we're shifting towards serverless computing. This emerging computing paradigm provides three main advantages. Firstly, it has high scalability, often implementing an unbounded scaling policy as a default auto-scaling mechanism. This means that when a query arrives and no idle container is available, the platform automatically initializes a new one. Secondly, it offers a pay-per-use, fine-grained billing system that charges based on resource usage rather than resource allocation. And thirdly, it simplifies resource management for users. With cloud platforms managing underlying infrastructures, users only need to upload their source code and data. Now, the emerging serverless paradigm inspires us to investigate whether graph processing can also benefit from it. To this end, we conduct profiling studies by executing Gemini, a state-of-the-art graph processing framework within simulated fast functions. This setting is referred to as SR. Additionally, we also include an extra setting named SD that enables direct communication between functions. The table below delineates a performance breakdown of three configurations in a representative graph workload executing the PageRank algorithm. We observe that direct migration to serverless can degrade performance, even with lower resource initialization latency and direct communication between functions. And second, graph I/O and preprocessing, often occurring during the cold start phase, can dominate performance. Additionally, we also conducted a profiling study focusing on memory footprints throughout the day. using the previously introduced real-world graph processing workload. For the figure below, the green line illustrates the allocated memory of serverless containers, whereas the orange line reflects the actual memory utilized during computation. Now let's say at 10 a.m. there's only one container in operation when a sudden security spike occurs. In response, the system quickly scales up to accommodate the increased demand for graph processing tasks following the unbounded scaling policy we outlined earlier. However, with the newly launched containers occupied by lengthy graph preprocessing tasks, the system has to initiate more containers to handle the remaining queries effectively. This is called excessive scaling, which arises when newly deployed containers cannot promptly address incoming queries, forcing the system to initialize additional containers to compensate for this delay. And finally, underutilized containers are recycled after a keep alive period. Given that those containers remain inactive after the query spike, the memory resources are left unused and thus wasted. Our conclusion is that unbounded scaling leads to the allocation of excessive resources, often resulting in wastage during the keep alive period. So inspired by our investigation, we introduced FaaSGraph, a code-design scheme that combines graph processing and serverless architecture. The following diagram illustrates the execution flow of FaaSGraph. Users start by uploading their function, graph dataset, and resource configuration. When a user sends a request, the scaling controller retrieves containers from the resource pool and loads the necessary graph dataset if required. Subsequently, the containers will begin executing iterative graph processing tasks orchestrated by a coordinator. Now, in the subsequent sections, we will delve into the details of our designs within FaaSGraph, including resource fusion, bounded scaling policy, and graph optimizations. Now, because graph datasets are typically large and the resources allocated to serverless containers are comparatively small, we need to coordinate multiple containers to handle a single graph processing task. Our key insight is that we can employ unified, fine-grained containers for graph processing while retaining scheduling flexibility. To achieve this, we introduce the container set abstraction, which includes fine-grained containers, each responsible for processing a subgraph. As depicted in the figure below, these containers can be distributed across multiple servers and co-located with larger containers or VMs from other users. This flexibility in scheduling enables us to leverage idle resources scattered across different servers to improve cluster resource utilization. However, the scattered containers could introduce extra communication overhead, which could degrade performance. To address this issue, we aim to recreate the illusion of locality by employing resource fusion. This involves simulating an environment similar to having a single large server instead of several small containers. Specifically, when containers are physically co-located, we can optimize load balancing by sharing their CPU resources. Additionally, we can also utilize the shared memory segments to establish fast data synchronization channels. For the containers located on different servers, we introduce message consolidation and async transmission to further optimize communication performance. Now, despite the introduction of container set, which acts as a scaling unit for resources, the default scaling policy still results in memory waste, as we outlined earlier. Moreover, the significant memory demands associated with graph processing exacerbate the problem. Thus, we propose a new bounded scaling policy. Our main idea is that rather than immediately allocating new resources, we wait for the current occupied resources to become available. As depicted in the figure below, upon the arrival of a query, it initially selects the shortest queue to join. Additionally, we also estimate the queuing latency for each queue to assist in decision making. Now, if the estimated queuing latency for current query exceeds the cold start latency, the system falls back to cold starting new containers. By adopting the bounded scaling policy, we effectively reduce the memory footprint by mitigating excessive container scaling. Simultaneously, we also enhance performance, as a prolonged cold start is replaced by shorter queuing latency. We have also revisited many design choices from previous graph systems. For example, we have introduced single mode may initiative message passing to reduce overall memory usage, and introduced fast graph loading to reduce preprocessing overhead. Due to the time constraint, we'll omit the details here. We have evaluated FaaSGraph across a range of graphs and graph applications, utilizing both a small cluster for one-shot query analysis and a large cluster for a case study. The specific resource configurations are outlined in the table. Additionally, we also incorporated several state-of-the-art graph system baselines for comparison. Our experiments show that FaaSGraph improves end-to-end performance by up to 8.3 times and reduces memory usage by up to 52.4% compared to state-of-the-art graph systems. Simultaneously, FaaSGraph demonstrates low memory scaling overhead as resources increase, and achieves a Pareto optimal balance between cost and performance. We've also conducted a case study using the query pattern we outlined earlier, where we compare FaaSGraph, Gemini, and a naive scaling version of Gemini. For this scaling version, we adjust the number of Gemini instances every 10 minutes based on priori knowledge of the query pattern. According to the table, introducing FaaSGraph can lead to up to 85.7% of daily monetary cost savings. The bottom left figure illustrates the tail latency during rush hours, showing that FaaSGraph, represented by the green curve, almost entirely eliminates the tail latency surge observed in the other two configurations. This is attributed to FaaSGraph's automatic scaling in response to the query workload, even when applying bounded scaling policy. Now, to summarize, IIS-based graph systems struggle with fluctuating workloads. Hence, represent FaaSGraph, a scalable, efficient, and cost-effective billion-age graph processing engine. By introducing resource fusion, bounded scaling, and graph optimizations, we aim to narrow the gap between serverless and data-intensive analytics. Our experiments demonstrate that FaaSGraph delivers substantial enhancements in latency, memory consumption, and cost efficiency compared to existing state-of-the-art systems. We have open sourced our code at GitHub. Thank you, and I will take your questions now.
Thank you for your impressive talk. So my question is that it is a well-known problem about the overlong keep alive duration will cause resource wastage, right? So there are some previous works. They try to optimize the instance pre-warming or adjust the keep alive duration to optimize such resource wastage. So what's the advantage of this bounded scaling over those previous works? Thanks.
Yeah, thank you for the question. I know there are many approaches optimizing the keep alive period and co-star pre-warming. They're all kind of bonded together. We made the research. We conducted this research based on the foundational auto-scaling policy that is proposed in the AWS. It's written in the handbooks, and I believe those optimizations in pre-warming also contribute to these memory saving issues. But I believe this also, in fact, in this work, this is a special case because the cost overhead is not only includes the resource initialization, but also includes the graph preprocessing and I/O, which is also very long. Much longer than the resource initialization latency. So this is a kind of dedicated problem area, and we can make a bounded scaling to reduce memory consumption. Yeah.
All right, thank you.
Questions?
Hi, Michael Giardino, Huawei. Nice talk. How do you do function-to-function communication?
Yeah, just direct communication. They know each other's address.
As in, you do this in Ada in Lambda or just?
No, we just build our own customized serverless
I see.
runtime. Yeah, because
so the cost numbers were just estimated based upon function where you show the AWS, the fast. Oh, this is so. Where is this? Where does the
cost? How do we estimate it?
Yes.
Yeah. So we're kind of taking the unit price in AWS Lambda and so we only take the unit price. So we kind of multiply it by time and memory consumption, and we derive the cost is derived.
So one more question. Is it okay? Yeah. Do you have any thoughts on how you would do this in a serverless system that doesn't have direct function-to-function communication?
Yeah, this is kind of an ongoing work I'm doing now. Yeah.
Okay.
For this work, we are kind of modifying the underlying serverless infrastructure, like you know, the resource fusion and container set abstraction were introduced earlier. So it's this we have to modify the underlying serverless infrastructure to better support the this kind of graph processing task. So we cannot deploy it on AWS Lambda. But for if you want to design system that support graph processing on AWS Lambda, we kind of have to use maybe an extra proxy or something for communication.
Right.
You know, a relay between functions to do this. And yeah.
Right. Thank you.
Great. Let's thank our speaker again. Who are this? Go ahead. So our second speaker is Rohan Mahapatra. He's a fourth-year PhD student at the University of California, San Diego. His research focuses on system for scalable and confidential machine learning inference and cross-domain multi-acceleration. Rohan is also the core contributor to the Jian system, our open source neural processing unit generator with full stack compiler, which was presented as a tutorial and ASPLOS past Sunday. All right.
Okay, thank you very much. Hello, everyone. My name is Rohan Mahapatra, and I'm very excited to present our work in storage domain-specific acceleration for serverless computing. Did you know that California's wildfire detection tool was among Time's best inventions of 2023? This tool uses drones and cameras to capture images and leverages artificial intelligence to detect fire and then alert the officials. It's a brilliant example of how technology can help protect our environment. These applications are generally deployed as serverless computing, where the application is designed as a chain of functions that perform a specific task. Serverless computing provides many advantages, such as allowing developers to create functions independently. Moreover, the service provider, which is the cloud, for instance, AWS or Google, they manage the infrastructure such as the servers, relieving developers from such tasks. And functions scale based on demand and ensuring optimal resource utilization without manual intervention. In fact, serverless computing's benefit has driven its adoption, with the market size growing from $3 billion in 2017 to a projected $22 billion in 2025. Simultaneously, at the infrastructure level, data centers are incorporating resource disaggregation, which refers to the separation of data center resources, such as the compute, storage, and memory devices, into shared pools that can be managed independently. Disaggregation provides benefits such as more efficient use of these individual resources, simplifies adding new devices, and increases system resilience by enhancing failure tolerance. And lastly, at the hardware architecture level, the failure of Dennard scaling and the effects of dark silicon has given rise to domain-specific accelerators. Data centers are integrating domain-specific accelerators that can provide significant compute speed up. Now, you'd think that the convergence of these trends will pay off big time, but domain-specific accelerators can because domain-specific accelerators can accelerate serverless functions, leading to an end-to-end speed up of the application. But that is not what we observe. When we execute a diverse set of applications on AWS Lambda, we find that a significant portion of the application runtime is spent on accessing storage over the network. In fact, remote storage access latency contributes to over half of the total runtime. The reason this happens is because in disaggregated storage data centers, reading data from the storage and writing data back to the storage requires RPCs for each function. Therefore, if we use a hypothetical accelerator that can provide, let's say, infinite speed up, the end-to-end acceleration is still capped at less than 2x as per Amdahl's law. To address this, we propose domain-specific computational storage for serverless computing, which is a serverless execution model that leverages a rather small but programmable accelerator within the storage to unlock the potential of acceleration in disaggregated data centers. We replace some traditional storage drives with domain-specific computational storage drives. These drives have a domain-specific accelerator integrated closely next to the flash media. Please note that our approach is not just limited to a specific domain or a specific accelerator type. So if we were to look at our execution workflow, we offload certain functions to the storage and perform computation within the storage itself. For those functions that cannot be accelerated, they fall back to the traditional mechanism of serverless execution. For instance, the data analytics, the last function, falls back to the traditional execution mechanism. So this hybrid approach ensures efficient use of utilization resources while maintaining the flexibility to handle a variety of functions. To achieve this vision, we need to address two challenges. First, how do we design an optimal accelerator that adheres to the stringent thermal and power constraints of the storage drive? And second, how do we seamlessly integrate this accelerator into the system stack? Now talking about the first challenge, storage drives have strict power constraint due to the limited PCI power budget, which is the exclusive source of power for these devices. Commercially available computational storage drives like the Samsung Smart SSD have a thermal design power or TDP of just 25 watts. And this power source is now divided between the flash array and the compute. To realize our idea, we choose neural network inference application since inference applications account for more than 40% of the serverless use cases today. Now, neural networks involve matrix multiplication operations and other operations such as activation functions, element-wise mathematical operations, data layout transformation, etc. To accommodate these operations, we use the open source Genesis project and implement a neural processing unit that includes a systolic array, which is a 2D organization of processing elements, and it is closely coupled to a vector processing unit to execute the other layers, for instance, the activation layers. This architecture is fully programmable, comes with its own instruction set architecture, and has parameterized RTL templates that can be customized. The RTL is open source and part of the Genesis project. Now, since we need to adhere to the stringent power requirements of the storage, we perform a design space exploration to identify the Pareto optimal accelerator that abides by the power limitations of the storage. To do this, we vary the number of processing elements, we vary the on-chip buffer sizes, we vary the memory bandwidth of the domain-specific accelerator. As the figure shows, the curved line shows the best performance, power, and area performance trade-off for accelerator configurations. By definition, what it means is the lines represent the system's most efficient configurations, which provides the maximum throughput for a given power or the minimum power for a given throughput. Now, after we identify the optimal accelerator configuration, we need to integrate the accelerator next to the flash storage, which we call as DSCS drive, as shown in the figure. The accelerator communicates directly with the flash array via a dedicated data bus. The DSCS drive also includes a DRAM memory as a staging buffer, aiding data exchange between the host CPU, the flash array, and the accelerator. We also have a DMA engine that ensures efficient data transfer within these components. Next, I'll briefly describe how we integrate the DSCS serverless into existing system software stack. The main objective that we had was to integrate this in-storage accelerator into the system software stack, addressing system software challenges without disrupting conventional operations in data centers, because data centers have a lot of applications that are running simultaneously. So at the system software level, we implement an OpenCL device driver and use a compilation stack that can compile ONNX models to the accelerator's instruction set architecture, because remember, our accelerator was fully programmable. The compiler first lowers the neural network's data flow graph, which is represented in ONNX, into an intermediate representation, and then uses this intermediate representation to generate code for different various accelerator configurations. Now, next, at the storage node level, we utilize the internal data bus that I showed earlier of the storage drive to perform these data transfers between flash media and the in-storage accelerator. To do this, we leverage the PCI memory address space to transfer data from the flash to the in-storage accelerator and vice versa, and use our OpenCL based programming driver. And At the serverless framework level, we implement first come first serve scheduling algorithm to offload functions to DSCS drives that hosts the in-storage accelerator. And when the function execution is over, DSCS serverless also smartly stores the function into the flash array instead of evicting it and fetching it back from the serverless function registry over the network when another request comes, thereby not only reducing the effect of cold start, but also relinquishing the expensive memory that are used to keep functions warm and are charged to the users. I won't delve into the specifics of these aspects, but I encourage you to read the paper for more details. So we deploy the system using OpenFaaS and open source serverless framework and employ Kubernetes for container orchestration and node health monitoring. To assess the effectiveness of DSCS serverless, we employ real-world latency-critical neural network applications. These applications represent serverless pipelines deployed on AWS Lambda. Let me go over the first benchmark, which is asset damage detection, which is used to detect damages in assets in industrial setting. This application consists of an image pre-processing function followed by an image classification, for instance, the ResNet 50 neural network followed by a notification service. And similarly, we have 7 other benchmarks representing a variety of use cases. These range from object detection using convolutional neural networks to transformer-based models for natural language processing tasks. We evaluate our proposed concept against a range of platforms. The first category includes traditional platforms that utilize the compute, for instance, a high-end CPU, GPU, or a FPGA, and access the storage over a network. The baseline CPU in this case represents AWS Lambda. These functions are high-end and exhibit a higher thermal design power or TDP. The second category is the conventional near storage platforms where the compute is located within the storage. And then we have the proposed platform where again the compute is located within the storage. Now, well, you see a lot of bars here and I won't go into the details of each, although I would love to explain them individually. But let me first explain what the figure is. The figure shows the speed up of various platforms normalized to the CPU baseline. The x-axis shows here the different benchmarks. Now, DSCS serverless notably improves performance compared to traditional platforms using remote storage, even outperforming a high-end GPU that accesses remote storage. This is largely due to the elimination of data movement latency. It also surpasses conventional near storage platforms by a significant margin. Next, let's look at the runtime breakdown that shows how different components such as the compute, the storage, and the system stack contribute to the end-to-end speed up. We observe that hardware acceleration on traditional platforms with GPUs and FPGAs significantly reduce the compute portion. However, network data transfer limits their speed up. The near storage platform address this data movement by moving compute close to the storage, reducing the data movement. However, the limited power budget for compute platform within the storage shifts the bottleneck again towards the compute. DSCS serverless not only accelerates the compute, but unlocks additional end-to-end performance gains by shifting the bottleneck from the compute and communication towards the system stack. This work isn't merely about designing a low-power accelerator for energy benefits. It has a system-wide impact. The figure shows the system-wide energy reduction in the y-axis normalized to the CPU baseline, and the x-axis shows the different benchmarks. Across the benchmarks, we observe a 3.5x system-wide energy reduction compared to the baseline CPU. Therefore, the limited power budget for computation in the storage for serverless requires a departure from conventional practices of integrating CPUs and FPGAs and calls for an alternative design approach of integrating domain-specific accelerators within the storage. We have more evaluations in the paper. Please check the paper for interesting results. Accelerated serverless computing can actually lead to degraded performance. Accelerators need to actually be considered in the context of end-to-end systems, modern programming paradigms, and innovations in data center design to unleash their impact. As I presented, our initial step shows that there is significant potential, and this holistic direction shows we can actually unleash the power of accelerators. Thank you very much for listening to me, and I'm very happy to take questions.
Hello, Johan from UAUC. I have a question about how do you enable sharing of these in-storage accelerators across functions? How do you ensure quality of service? How do you ensure security? How that works?
Okay, that's a nice question. So we use the exact same scheduling mechanism as a traditional serverless infrastructure uses. The way we share is because serverless functions are independent of each other, we can have multiple DSCS drives, and then as each function request comes, actually in the paper we do at scale evaluation where we use a Poisson distribution trace, and then what we do is we use our scheduler to intelligently map, not intelligent, but we map the requests to DSCS drive that are available. And the best part is, if we don't have any DSCS drives, let's say it's a trade-off between cost and performance, right? Let's say we don't have any DSCS drives, then we can fall back to the traditional execution mechanism, and that's what we do. So some of the functions are accelerated, some of the functions are not accelerated, but still executed, not stalled.
Okay, so if you
No.
So if you have lots of queuing on your storage, do you decide to
I didn't get the.
if you have lots of queuing in the storage, do you
Yes.
still go there or you compute it
No,
locally?
we fall back to the traditional
Okay.
mechanism. So actually, we in the results we show that the queuing at the CPU increases. I think in the evaluations we assume 200 DSCS servers which are available, and then I think the total load is more than 1,000, which is 5 times more. And then we do queue some, but actually we improve performance over the baseline.
And the final one is how would you combine this with caching schemes?
In-memory caching schemes?
Yes.
In-memory caching for serverless are expensive. First of all, you need explicit management of in-memory caching. Because in serverless functions are stateless, I can't predict how many requests I will be getting. There are works like Jiffy from UT Austin, which do in-memory caching, which is orthogonal to our work.
Yeah. I mean,
But
like how would you, for example, fast cache and this, how would this combine?
how do we combine with in-memory caching?
Yeah, how, like if
So
you
caching
have
the
data
caching the
Data.
intermediate data, you mean, right?
Yes.
Caching. In a way, actually, we do that. We also have evaluations where, let's say, 2 of the functions can be accelerated. What we do is we use the same DRAM, we use the same intermediate, the result, and then we co-locate the function on the same DSCS drive. So that way, we actually leverage caching.
Okay, thank you.
Thank you.
Let's thank our speaker again. Go ahead and set up. Our third speaker cannot present in person due to the visa issue. So as we set up the computer, let me introduce the speaker. The third speaker, Guowei Niu, is a 30-year graduate student at the Tianjin University and advised by Professor Lai Pinzao. And his research focuses on data processing unit and serverless computing. And over the past 2 years, he has been interested in addressing data transfer issues in serverless computing by leveraging DPUs. Yeah, we can start.
Hello, everyone. I'm Guowei. Today, I'm glad to introduce our work. We are CPU-enabled direct data transfer for serverless computing. This work was carried out by Tianjin University in cooperation with Kinzer. In this work, we focused on the data transfer problem in serverless computing. In serverless, applications are composed of fine-grained functions and executed in a predefined directed acyclic graph. Due to the stateless nature of serverless computing, functions with dependencies must transfer data via the third-party forwarding method. That is, an upstream function has to store intermediate data into external storage and require the controller to orchestrate interaction with the downstream function, which retrieve the data from storage. This method couples control flow and data flow. To evaluate the data transfer efficiency of third-party forwarding method, we conduct a set of experiments, use media service as a benchmark. Our findings reveal that the third-party forwarding method, which couples control flow with data flow, resulting in a high communication ratio, auto-scaling failures, and high CPU usage for data transfer control. To mitigate this issue, some optimizations are proposed to accelerate the control flow and data flow, respectively. For example, they use more effective inter-process communication mechanism to replace network communication between the controller and the functions, and employ shared memory to avoid data copying between functions. However, this optimization have limitations. First, they are only suitable for co-located functions. In fact, in product system, it's not always feasible to avoid deploying function across nodes. Second, they still follow the couple design. We have analyzed that the couple design not only prolongs transfer latency, but also handles throughput and consume a lot of CPU resources for data transfer control. To address these limitations, we explore decoupling the control flow from data flow by establishing stateful connection between functions, enabling direct transfer between them. Once built, functions, regardless of their location, can communicate with each other directly through stateful connections, bypassing the controller. In the following, we will present the details of Fuyao, a serverless system that enables direct transfer between functions within or between nodes. Fuyao also explores the leverage of data processing unit, that is DPU, to improve data transfer efficiency further. However, achieving such a system is not easy. We need to solve three challenges. First, establishing stateful connection between functions introduce a non-negligible overhead. In scenarios with sparse invocation, traditional third-party forwarding method could still be effective, ensuring compatibility with different data transfer methods pose a challenge. Second, DPU has a weak processing power compared to CPU. Naively placing DPU on the critical processing path will result in significant latency. Therefore, how to correctly use DPU to strike a balance between latency and CPU resource consumption is a challenge. Third, after introduce a new data transfer method, determine the optimal data transfer method for different scenarios is a challenge. Here, we present an overview of Fuyao, which can be separated into data and control plane. The control plane comprises the gateway internode engine. The data plane consists of many function instances. Next, we will introduce how Fuyao addresses the three challenges. Use these modules. To solve challenge 1, Fuyao set a sidecar for each function instance. The core design of the sidecar is a state machine consisting of 10 states. By transitioning between states, it can support both third-party forwarding method and the direct transfer method. Note that direct transfer is implemented by DTC, that is, directed transfer channel. As shown in the figure, function sidecar can collaborate with internode engine to establish DTC between co-located functions. To solve challenge 2, we explore the principle of DPU offloading. NVIDIA Blue Field has multiple SoC core. Adjacent to the NIC, and SoC core has much slower processing speed compared to the house CPU core. Experimental results show that low compute components can be offloaded to DPU without a significant increase in latency. More detail in our paper. We implement internode engine, which contribute to establish DTC between functions across nodes. It's no longer activated once DTC has been established. Due to its low compute nature, we offload internode engine to DPU for saving CPU resources. Moreover, RDMA in DPU is used to accelerate internode DTC. Now let us discuss challenge 3. Fuyao provides 4 different data transfer methods to cater to diverse data transfer requirements within cross nodes. These methods involve DTC methods as well as third-party forwarding methods. To conceal the complexity of data transfer method selection, we introduce a policy to automatically determine the optimal data transfer method. Our policy is as follows. First, check if a DTC exists. If so, use it. Otherwise, if there are potential benefits, create a DTC before transferring data. Otherwise, use third-party forwarding method. For more details, please refer to our paper. We implement Fuyao on Netcore, a SOTA system. Fuyao's implementation consists of two parts, the CPU part and the DPU part. It comprises approximately 17,000 lines of code, primarily written in C and CPP. We conduct all our experiments on a cluster consisting of two machines, each equipped with NVIDIA Bluefield DPU. We choose the three applications from Serverless Bench and Desktop Bench as our benchmarks. We compare Fuyao with OpenFast, Netcore, Film, and Fuyao without DPU. Fuyao without DPU is a variant of Fuyao without utilizing DPU. We consider three metrics: latency, throughput, and resource consumption. We first evaluate the data transfer latency between two arbitrary functions, our experimental, so that both variants Fuyao significantly outperform other systems. Fuyao can speed up 2.7 to 15.4 times compared to the second best system. We evaluate the average latency. Results show that Fuyao can reduce the average latency of this benchmark by up to 124 times. For this benchmark, Fuyao can reduce the 99% latency by up to 76 times. Next, we measure the maximum throughput. In the evaluation, we have disabled the auto-scaling feature and set the fixed number of function instances. Results show that Fuyao can improve throughput by 1 to 2 orders of magnitude with the same number of function instances. We measure the CPU usage. Results show that Fuyao's control plane consumes no more than 0.4 core at QPS equal 500, reduce CPU usage by over 80%. This reduction results from separating the control flow from the data flow, significantly decreasing control plane involvement. We further evaluate Fuyao's performance, use production trace from Azure function. We measure the latency of media service with both DTC enabled and disabled. After enabling DTC, Fuyao can reduce the mean latency of media service in both periodic and birthday trace by over 80%. Finally, let's focus on the overhead Fuyao. First, we conduct a breakdown analysis of the overall latency in media service and the varying QPS. Results show that Fuyao can reduce the communication ratio from over 70% OpenFast to less 28.3%, leading to overall latency reduction. Next, we measure the handshake overhead for creating DTC in this benchmark. We found that the handshake overhead is high in lengthy or high fan-out workflows. In these cases, we can mitigate this overhead by improving the reuse rate. Lastly, we evaluate the impact of RDMA scalability issue on internal DTC, which is based on RDMA. We found that the scalability issue of RDMA has a limited impact on cross-node DTC. In summary, Fuyao aims to improve the data transfer efficiency in serverless computing. It provides for data transfer method as use direct transfer for function pairs that communicate frequently. Fuyao demonstrates significant improvement in latency and throughput while reduce control overhead. That's all. Thanks. Hi everyone, I'm Wang, author of Fuyao. If you have any question, you can ask me. But I'm not a I'm not a native English speaker, so please speak slowly.
Go ahead. Any questions? So I have one question. When you use the DPU to speed up the serverless computing, how do you enforce the performance isolation for different serverless functions?
Different function. In fact, we mainly use the DPU's capability, including SOC and IDMA. Um, uh, 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 to get
Okay, thank you. And let's thank our speaker again. Yeah.
就是
Okay, our last speaker is Chuhao Xu, and he's a first-year PhD student in Shanghai Jiao University, and his research interests lie in the cloud computing, especially the serverless computing. Now he will present the data flow design in serverless computing.
Hi, I'm Hao from Shanghai. Okay, sorry. Let me check. Okay. Hi, I'm Hao from Shanghai Jiao University. Today, I will introduce data flow, exploiting the data flow paradigm for service workflow orchestration. First, I will briefly introduce what service is and how we usually run a service application. The term serverless has become a hot topic in cloud computing, but why do we need serverless? First, let's look at cloud providers. They have been struggling with a phenomenon known as diurnal patterns with resource underutilization. Second, from the perspective of developers, long-running instances may incur unnecessary cost. In addition, they're also suffering from complex environment management. That's where serverless come in. It provides a platform-managed on-demand service model. Specifically, according to Berkeley's view, serverless equals to FaaS plus BaaS. Developers upload their codes as functions to a FaaS system. User triggers a function through events. The FaaS system then allocates computing resources and interacts with the backend services to execute functions. So how do we actually run the serverless applications? The answer is serverless workflow. This means to grouping together multiple functions in a seamless flow, guided by preset control flow. The examples include video processing, ML fine-tuning, and so on. Next, I will discuss the inefficiency of control flow and what happens if we use the data flow. In general, under the control flow paradigm, there is a global orchestrator maintains the states of all functions and triggers them in a sequential order based on user-defined control dependencies. When no predecessors of a function are complete, the orchestrator triggers it for execution. Take function B as an example. It is triggered after function A is complete. Then B's input data is loaded from the backend storage. And if B needs to transfer the output data to the destination function C, it must store the data in the backend storage and C reloads it. In the process described above, the CPU is usually idle during the data transfer, and the network is usually idle during the execution. We then run 4 real-world service workflows on production platforms, and we find 3 main limitations with control flow. First, the double transfer of the intermediate data among the source function, the backend storage, and the destination function results in heavy communication overhead. Second, by default, a serverless orchestrator cannot schedule a container to run multiple function invocations concurrently, and the sequential steps of executing a function will idle either the CPU resource or the network resource. Third, The state management overhead and the control flow-based triggering make the actual trigger time of a function later than its ready time. The data flow paradigm has the potential to resolve the problem. Following the data flow paradigm, a data flow graph describes the data dependencies between the functions, and the function starts to run immediately once all its input data is ready. Based on the data flow graph, the intermediate data flows asynchronously to the destinations as soon as the input data is generated from the resource function without relying on the backend storage. And this feature also allows for efficient overlap of computation and communication. Moreover, in this way, each function determines whether it can start to run independently in an out-of-order fashion without a centralized orchestrator. However, designing a serverless workflow scheduling mechanism based on the data flow paradigm faces three main challenges. First, the computation and data passing should be decoupled. However, current service frameworks do not support such operation. Second, the workflow engine should fundamentally support the decentralized function triggering based on the data availability, while current frameworks often use a centralized orchestrator. Third, the direct data communication mechanism should be carefully designed to support the implicit data plane. Next, I will briefly introduce the design of data flower. Data flower deploys the data flow schemed scheduling engine. A container of a function is abstracted into a function logic unit, the FLU, and the data logic unit, the DLU. So the FLU actually runs the function, and the DLU receives the input data from the function and pushes the output data to the destination functions. Moreover, between each source and destination function pair, a pipe connector is used to transfer the intermediate data. And the left figure shows the programming model in data flower that supports the computation and data transmission separation. Data flower provides an interface for function to declare the data to be handled by the DLU. So the FLU then just executes the function, and the DLU receives the data from the function FLU and transfers the data to the destinations. The right figure shows the execution of a data flow graph. The FLUs and the DLUs of a container run asynchronously, and multiple FLUs of a function can also run in a pipeline to maximize the parallelism. So with the FLU and DLU abstraction, the data transfer of a function now becomes an asynchronous operation. However, it may result in queuing, and the upper figure shows such an example. In this figure, the FLU receives 3 requests per second, but the DLU daemon is only able to transfer the data to the destination for 2 requests per second. So in this case, the queuing may result in severe long response latency. We therefore propose a pressure-aware function scaling mechanism as shown in the bottom figure. The FLU dispatching rate is now limited to the maximum DLU consumer rate, and when higher loads arrives, the engine follows the serverless manner to scale out the containers horizontally to handle the remaining workflow invocations. So up to now, the computation and communication are decoupled. However, the data flow graph is still unknown as the destination of a function's data is not defined. Back in the control flow, the developers need to define the function triggering relationships. Similarly, now in data flower, the developers also need to define the input data and the output data, including the data destination of each function. So as an example, the left figure shows the pseudocode of workflow definition of benchmark word count. However, a service workflow is still not able to run now with only the data flow graph. This is because a function does not know the exact location of its subsequent functions. So to resolve this problem, data flower obtains the function deployment information from the load balancer. And this figure shows the way to parse the data flow graph. Data flower deploys a workflow scheduling engine on each node. Each engine parses the data flow graph based on the data workflow definition and the function deployment. So with the data flow paradigm, a function is triggered to run based on the data availability. A container will not be assigned until all of its input data of a function is ready. So to cache the input data for a function before it can be triggered, we propose a host container collaborative communication mechanism. Data flower uses a data sink on each host to cache the input data of all the functions on the node. To minimize the memory overhead for data caching, data flower proposes a hybrid mechanism to perform fine-grained data management in the weight match memory and alleviate the data backlog. First, as soon as all the destination FLUs have received the data, this cached data can be proactively released from the weight match memory. Second, each data is also given a time to leave threshold, and it will be offloaded to the disk once timeout. Lastly, let's take a look at how data flower behaves. We conduct the experiments on a 5-node cluster with 4 benchmarks, and we compare data flower with SOTA serverless workflow systems, the FastFlow and Sonic. Our evaluations demonstrate up to a 35% reduction in 99 percentile end-to-end latency and a 3.8 times improvement in peak throughput, since data flower directly transfers intermediate data and invokes the subsequent functions in advance. It also reduces the memory resource usage by up to 69%, as the pipe connector handles the time-consuming data transfer, while traditional control flow pattern requires to perform the time-consuming data transfer within the container, taking up valuable container resources. Considering that data flower sends the output asynchronously through the DLUs, the proposal of DLUs have actually never become a bottleneck. Thanks to the pressure-aware mechanism, we can identify the pressure of DLUs in all cases and scale out when they are overloaded. Meanwhile, data flower can trigger each function 11 milliseconds earlier than other work, and our proactive release mechanism have also reduced the intermediate data cache overhead by 93% in average. Finally, we give our conclusion and discuss the future work on data flower. Data flower mainly resolves 3 problems to realize the data flow paradigm in service workflows. First, we propose the data flow-based paradigm and execution model in serverless to decouple the computation and transmission with the help of pressure-aware scaling mechanism. Second, through the data flow-based workflow definition, data flower implement efficient data plane synchronization and container management. Lastly, data flower incorporates a set of data flow specific suites, including the pipe connector and data sink to support direct data transfer and data lifetime management. Looking ahead, with the FLU and DLU abstraction, we can offload them to many heterogeneous compute devices. Meanwhile, as we now know the data dependencies graph, we can also pre-warm the subsequent containers just in time. You can refer to our paper for more details, and data flower is also open source on GitHub. Thank you.
Yes. I have one question is that in reality, when you access the storage, the latency will vary, right?
Yeah.
Will vary. So in your model, can you comment how your model can tolerate the performance, varies?
You mean how to detect the pressure, right?
Not only pressure, but when you draw the graph, right? So the dependency may change, right? So on real time, and also the latency for the dependency will also change, and how your model can tolerate this.
Well, actually, I will first answer the question that what will change if the data dependency graph change. So actually, this is a limitation of our work, since we need the end user to predefine the data flow graph, and the flow must be preset. But we also allow for some simple judgment, like we also offer the if condition, like a data can within a check like whether a value is greater or less than value. So we offer some branch condition, the definition language in YAML, right? So we use
as a fly.
Yeah, Rohan from UC San Diego. So the benefit of serverless is horizontal scaling. So let's say function 1 and then function 2 got replicated or scaled horizontally at like runtime, right? Just because we had a lot of requests. So how do you handle that case? Let's say we had like, let's say we have 10 function 1s, but let's say 1,000 function 2s because function 2 was the bottleneck. So we had to scale it horizontally. So how do you find the addresses of the subsequent dynamically scaled function 2 at runtime?
So you mean how to find the destination address, like the
Yes.
specific node, right?
Yes.
So actually, in our model, in our preemption, we think that when a request comes, the upper load balancer will schedule some nodes to run this request. So when a request is come, all of this function, the execution location of the function is set.
So is it
So to handle the large scale solution, we can assign different nodes for different requests.
So you always have warm functions, basically.
Yeah.
Okay. Thank you.
Any more questions? Okay, great. Let's thank our speaker again. I think this is the end of this session. We have a break.